All right. Well, it is my great pleasure to be introducing Andreas Crivellin. And so he got his PhD at the Karlsruhe Institute of Technology, and then did postdocs at Bern and CERN, and now at the Paul Scherrer Institute, and also in Zurich University as a professor. Did I cover everything there?
Yes, yes.
Okay, great. I reached out to Andreas because I saw his work on anomalies in particle physics, and it is just an amazing work. We all know that the standard model is not complete because it doesn't have dark matter, for example, but at what point will we see experiments that disagree with the standard model? And, we're seeing many signs of these experiments that disagree to certain degrees. And that's what this is about, anomalies in particle physics, and bringing it all together, so many different areas to see all these different experiments and that disagree with the standard model and trying to have a coherent picture. This is what Andreas has done very well. And so I'll hand it to you.
Thank you very much for the very kind introduction. Is this a laser pointer?
You switch it on. Does it work? Yeah, there we go.
It doesn't work on the screen.
Yeah.
Okay. So
You have to use your.
should I do it from the?
Yes.
That's better. That way the Zoom people can see as well.
Okay, perfect. Okay, so so again, thank you very much for the kind and already perfect introduction. So this saves me another 2 minutes. So I want to talk about anomalies in particle physics. But as you said, there are so many anomalies, and it's such a broad field now that I think I cannot cover all of them in detail. So my plan was to focus on the anomalies which are related to new Higgs bosons, so new scalars with somehow similar properties than the standard model. And as I've heard, you are expert in quantum studies, and maybe your quantum field theory and standard model courses have been some years ago. So please interrupt me at any time if if I assume you know something you don't, and if you have questions, also please interrupt me at any time. I'm very flexible. I can explain in more detail what you want to know, and if I don't finish everything, that's perfectly fine. So please make it interactive and let me know if there's anything you want to know. Okay, so still, I think a brief review of the standard model might be helpful for everyone. So we know that matter is made out of fermions, namely quarks and leptons. The quarks have strong interactions, so they interact via gluons in the theory which is called quantum chromodynamics, QCD. And you probably know QCD is confining, so at low energies it's non-perturbative. At high energies, fortunately, it is perturbative. So there I can calculate predictions with perturbation theories, but at low energies, it's confining, and I need non-perturbative methods like simulations with lattice QCD to get predictions. So you for sure know that up and down quarks make together protons and neutrons, and they are held together via the strong force, via QCD. Now, protons and neutrons are also held together in the nuclei via QCD, but there's only a small remaining force, like you might know from chemistry, the van der Waals forces. So within the proton and the neutron, the QCD color charges are quite well shielded, but then there is some residual force left, and this is what keeps protons and neutrons together within the nuclei. Then, of course, we have electrons, but there is also always the neutrino. And now what is important is that we have 3 copies of these fermions. So the first generation fermions make up, in principle, all the matter around us, but surprisingly, they come in 3 copies called generations of flavors, and they have, in principle, the same properties, just that they differ in mass. Now, of course, in practice, this makes a huge difference. While the first generation fermions are stable, at least to a very good approximation, they are stable. Nobody has ever observed proton decay yet. The second and third generation fermions are heavier and unstable. So, for example, a muon decays into an electron neutrino, and a muon neutrino. And also all the other stuff, the heavier it is, the shorter its lifetime. So, for example, here, the top quark, this is the heaviest particle of the standard model with a mass of around 174 GeV, decays so rapidly that it cannot even hadronize. So it doesn't form bound states like the other quarks do. So just to give you a little bit a feeling of the masses here. So 1 GeV is nicely the mass of a hydrogen atom. So a proton is something like 170 times heavier than a hydrogen atom. We have finally the Higgs boson. I will come to this in more detail. This is around 125 GeV. The bottom quark is around 4 GeV, and all the rest can, in many cases, be even assumed to be massless. That's a quite good approximation. The neutrinos are, in fact, exactly massless in the standard model, but we know that this is not the case. Small neutrino masses have been observed, so this is already a proof that the standard model cannot be complete, but must be extended. As I will also briefly mention later, and as you said, the problem is we know it must be extended, but we don't know how it should be extended. Neutrino masses here are a good example. You can add right-handed neutrinos to give masses to the left-handed neutrinos of the standard model. But this you can do from the keV to the multi-GeV scale up to nearly to the Planck scale. So we know the standard model has to be extended, but we don't know how. And this is why we need more experimental evidence. Then another two things here is the W and the Z boson. So these are the mediators of the weak interactions. And they are, for some sense, the strangest particles in the standard model because they are quite heavy, 80 and 90 GeV, and they receive their masses from the Higgs. I will also come to this in a little bit more detail. And then, of course, here we have the photon for the electromagnetic interactions, the gluon for the strong interactions, so only quarks interact with gluons, but the photon interacts with everything that has electric charge, so, of course, electrons, muon, taus, and up quarks, down quarks, and the heavier generations. Okay. So, now let's have a little bit a closer look at the Higgs boson, because this is what the anomalies I will focus on. If you are interested in other anomalies, I have a review plot and I have a lot of backup slides, so please ask me, but I want to zoom in on the Higgs because I think it's most interesting. It's also my most recent work. So I don't know, are you familiar with Feynman diagrams?
Sure.
All of you? Okay, perfect. Then the slide is even too easy. So photons interact, for example, with electrons via the electric charge. So the electric charge is the coupling constant of photons to electrons. For Higgs interactions, the coupling constant is what is called the Yukawa coupling. And then the important thing is that the mass is always proportional, at least in the standard model, to the Yukawa coupling times the vacuum expectation value of the Higgs field. So the heavier the particle, the bigger the coupling of the Higgs boson to this particle. Now, the mechanism how the Higgs boson gives masses to all fundamental fermions and also to the W and the Z boson is the mechanism of spontaneous symmetry breaking. So if I had classic rod here for pointing, then I would show you in more detail, but I guess you know the concept. So if you have a rod, it's of course rotationally invariant. Now, if you bend it with force that is not in the same direction as the rod, your system is not rotationally invariant anymore, and you explicitly violate the rotational symmetry. This would be explicit symmetry breaking. But now what happens in spontaneous symmetry breaking is that you apply the force in the same direction as the rod. So the system is still rotationally invariant, but once you pass a critical threshold, the rod will bend. And then the symmetry is broken spontaneously. But the important thing is it could be broken in any direction. So if you consider the possibility that it could be broken in any direction, we recover the original symmetry. So the symmetry is in some sense still there. It's just not visible from the external system. And this is exactly what is happening with the Higgs boson in the Standard Model. So if you see here on the right, this is the famous Mexican head potential of the Higgs boson. And you see it is rotationally invariant. However, as you also know in quantum field theory, you're always sitting at the vacuum, so the lowest possible energy state. And this is not at zero field configurations. This is somewhere down here in the valley of the Higgs boson. And now, if you are sitting in this valley, it doesn't look rotational invariant anymore to you. And so this is what's happening in the Standard Model or in our world. We are now at temperatures in this universe where we can't see the full symmetry of the electroweak energy interactions anymore. We are sitting down here in this valley. And from this valley, it looks like electroweak symmetry is broken. So W bosons, Z bosons, and the fermion have masses. But if you went at very high energies, where you can disregard the masses of the fermions, then your symmetry would be restored. Anyway, so what you can see here is that this gives you rise to a vacuum expectation value. And this vacuum expectation value, if you multiply it by the Yukawa coupling, gives you the mass of the fundamental particle. This is true for fermions and gauge bosons, but it also tells you, if you know the mass of a particle, you know it's coupling to the Higgs boson, at least with the Standard Model.
And indeed, as you pointed out, if you go back to your slide, the symmetry is still there. You can go around the bottom of this bowl, and I can see there's these Goldstone modes, right?
Exactly, perfect, yeah. So I wasn't sure what to expect, but I see you know really a lot about it. Yeah, exactly. So the Goldstone mode is the mode where you don't have to go uphill in the potential. So the Goldstone mode is exactly around the bottom of the Mexican head, but then if you go perpendicular to it, there you have a quadratic potential, and that's the mass. Yeah. Exactly, that's the mass of the Higgs boson. Okay, but now the question is, how do we find the Higgs boson? So how did we find the Standard Model Higgs boson? And in similar ways, how can we find future Higgs bosons if there's hopefully more than the Standard Model? So what one does is one collides proton at very high energies. And here now the important thing is that at high energies, you can even approximate to some extent protons by gluons. So the higher the energy of a proton, the higher the probability that you find a gluon within it. So at high energetic protons, most of the energy is carried by gluons. So in some sense, the Large Hadron Collider at CERN could be considered as a gluon collider, because you take the gluons out of the protons, and then with this you can produce the Higgs. So here you see the diagram. So we have the proton, and at high energy it's quite likely to find a gluon in it. Now, the gluon couples to the top quark, of course, because the top quark is charged with a color. And then you have to close this loop. So this is called a loop diagram. So this is a quantum correction. And then the Higgs couples via the top Yukawa coupling to the top quark. Now, keep in mind, the top mass was 174 GeV. Interestingly, the vacuum expectation value of the Higgs is of the same order. So this is an order 1 coupling, but you pay a price from the loop suppression. A loop suppression normally gives you something like 1/16 pi squared just from the integration. So this is the reason why it was so difficult to find the Higgs boson, and why it took something like 4 generations of colliders from the invention of the Standard Model till the Higgs boson was discovered, because it is the first particle ever observed that is generated by a quantum correction. All other particles we ever discovered were directly produced from colliding quarks or electrons. Here, this is the first time that it's produced via quantum correction.
Those are all tree level diagrams, whereas this has a loop in it.
Exactly. Exactly. So this is a loop. So it's a quantum correction suppressed by 1/16 pi squared. And this is the reason why it was so difficult to find the Higgs boson.
Now, ordinarily, I would say the loop was suppressed by the coupling constant in front of the coupling. So why is it? Are you talking about the dimensionless units, the 16 pi squared, or?
So the 16 pi squared comes from the integration over 4-dimensional space. And then you are absolutely right. There are dimensionless coupling constants, but in this case, they are all order 1. The strong coupling is order 1. The Yukawa coupling is order 1. So you don't pay a price.
So like in QED, for example, you like 1 over the fine structure constant or something.
Exactly.
Like that.
But here it's bigger. So fine structure constant is 1/137. And here it is only GS, so it's only 1/10. So it's,
Got it.
But you can still do perturbation theory, fortunately. Okay, now I can produce a Higgs, but I also have to observe it. And here, the golden mode is its decay to light. So it's decay to photons. This is mediated again by a top quark, but it would also be mediated by W boson. Now, again, this is a quantum correction. This is a loop process. So it is suppressed. However, because finding 2 very high energetic photons at the LHC is quite improbable, it is a very good discovery channel because the background is so low. And now, how are you doing it? This you can see here on the diagram on the right. From the energy of the photon, you can reconstruct the invariant mass of this pair. And because this is a Lorentz invariant quantity, so it doesn't change if your system is boosted, you can reconstruct the mass of the decaying particle from the invariant mass of this photon pair. Now, you see, you have a background, but this is just continuous here. Interestingly, we can't really calculate this background. We are still just fitting it to data. So we are fitting a continuous function to the background. And then what we do is we search for a peak on top of it. And this peak on top of it means you had an on-shell particle that decayed. Now, you see, this peak here has a finite width, but this doesn't come from the Higgs boson. The width of the Higgs boson is very small. This comes from effects like acceptance, detector resolution, and so on. So this is an experimental effect that the peak is not extremely narrow.
And by mass of the 2 photons, you just mean the energy, I guess, because there's no rest mass.
No, it's the invariant mass of the pair. So you square you calculate Q nu of the you take the 2 photons, you P1, P2. It's the invariant mass of the pair, of course. The photon itself is massless.
So you take the momentum, the 4 momentum, and you take their difference and then square it. Is that right? Or how do you calculate it?
I think it's just P1 mu P2 mu, and it's just the times P minute, if I'm not mistaken. But I think there's no difference. So it's just you take one photon Q mu, the other one is just the.
And that's the Q is the momentum.
It's the 4 momentum, yes, of the.
So you take their direct product.
Yes, you just take the direct product. I'm not 100% sure. I have to look it up.
Well, the way I think about it is in the center of mass frame.
Yeah.
You have 2 photons that are going on opposite directions.
Yeah.
So if you add their 3 momenta, that's 0.
Yeah.
But you also have to add their energy.
Sure.
And if you add their energy, then what you have is and energy and no momentum. And so that's the mass. That's where the mass comes from.
Okay.
Yeah. It's so of course, if you did Q1 squared, it's 0. Q2 squared is also 0, but Q1 times Q2 is not 0 anymore.
Yeah. Great. Thanks.
Okay, so here you can see the nice peak, and if you have this peak, you know there's a new particle. Now, the question is this Higgs that we found really the Higgs of the Standard Model? One way to check it is, does it really couple to all fermions and gauge bosons proportional to the mass? And as you can see here in this plot, at least to a good approximation, it does. So it's a straight line. It works quite nicely. But there's still the question, is there physics beyond the Standard Model? Now, as we already heard in the introduction, we definitely know there is. We already mentioned neutrino masses, but there are also things like dark matter. So why are the rotation curves of the galaxy bent? So why are they outside faster than expected? And another thing is, why is there matter-antimatter symmetry? So why does matter around us exist at all? If everything were symmetric, you would expect that matter and antimatter are linear, and nothing would be there. And for this, in general, what you need is additional CP violating interactions. But anyway, you see, you have to extend the Standard Model. We can only account for 5% for it, but the question is how? And just these observations are not enough. So we really need a new physics discovery to make further progress. How can you do this? So there are 3 frontiers. There's the cosmic frontier. This means dark matter, dark energy, and so on. The energy frontier, so here at the moment we only have, unfortunately, the Large Hadron Collider at CERN, but we are all very much hoping for future colliders like CEPC in China, FCCEE, or CLIC at CERN. So this would be very important for the future of the field. And we have the intensity frontier, so these are precision tests. So here what you do is you don't look directly for a new particle, but you look for precision observables, and you can test quantum fluctuations via this. So direct searches for new physics, this we have already seen for the Standard Model Higgs case. So here what you do is you fit a continuous spectrum and you look for a peak on it. And if there's a peak, you have it. Sounds easy. It's of course in the end more difficult than you think. So the good thing here is if you find a peak, you know the mass of the particle. So that's very good. The problem is you are limited by the energy of your collider. And at low energies, you normally have quite a lot of background. So you have a lot of accidental events if the energy is not very high, and it's difficult to distinguish new physics signal from the background. And what I will also come to it later, there can be new physics signals which are non-resonant. So if you have invisible decays in your event, so for example, neutrinos. You know, neutrinos are extremely weakly interacting particles. We cannot see them at the LHC. You need these huge underground detectors to see neutrinos which come from the sun. And
not entirely true. Phaser. The phaser experiment sees neutrinos from the LHC.
Okay, 1 or 2?
Okay.
Okay, you're right. Phaser has seen, I think, 1 or 2 neutrinos from, but this statistics is by far insufficient to make searches. Yeah, but you're right. Phaser, I think they have 2 events or so. Yeah.
Okay.
Yeah. Yeah. So you're limited by the energy, and if you are low energies, you have a lot of background. So that makes it difficult. Indirect searches, in a sense, are easier. You just do an experiment. You do it very precisely. You compare it to your hopefully as precise Standard Model prediction. And if they don't agree, there must be new physics. But of course, this is not that easy. G-2 of the muon is a good example. There have been this tension for years, and experimentally it has been confirmed, but now it turns out that there might have been a problem with the calculation of the background for the experimental for the experiments you needed to determine a Standard Model prediction, so it doesn't look too good, for example, for G-2 of the muon.
I would love to talk with you about this later. You're not going to cover that in this talk, right?
I can cover it. I have backup slides, but
okay. Well, let's talk about it.
I crossed it out from my list of anomalies.
Okay, but I would love to talk with you about that later.
Okay. Good. So, what is an anomaly? In general, a deviation from established rule. Here, a deviation from the standard model prediction. Now, as I don't have the time to cover all anomalies, you see here, I already crossed out G minus 2 of the muon because of the bad experimental situation. What I want to focus on is new physics at the electroweak scale. So new physics with masses similar to WC boson and the Higgs boson. For all of the rest, we can talk later and you can ask me some questions. So, as said, I will focus on the Higgs sector, and there are several reasons for that. So, it's the origin of what are called the internal problems of the standard model: hierarchy problem, flavor puzzle, vacuum stability. So, hierarchy problem means why is the Higgs at 10 to the 2 GeV and not at the Planck scale of 10 to the 19 GeV? Flavor puzzle means why do we have 3 generations and why are the masses of the fermions so very different from the electron of 500 keV to the top quark of 170 GeV. And vacuum stability just means we don't know if the standard model vacuum is stable. So the Mexican head potential, we don't know if this is stable up to all energies. So it could be that the vacuum is decaying. Exactly.
And there's also a puzzle why the Higgs is so much heavier than the rest of the particles. Isn't that why it took a long time also to find it, because it's much heavier?
It's a little bit lighter than the top quark. It has 125 and the top quark has 174. So, but you're right, it is much heavier than previously expected. Because before we knew about the top quark, people expected that the Higgs boson could have similar masses than the bottom quark.
Yeah.
And, or before we knew about the W and Z. So, and you're right, it's also a bit lighter than expected from supersymmetry. In supersymmetry, people were hoping for a little bit heavier Higgs. But, I mean, this is a tuning of, let's say, something like maybe 20, 30%. But this fine-tuning problem is really orders of magnitude. It could be anywhere between the electroweak scale and the Planck scale. But once you fix the Higgs mass at the electroweak scale, then it's natural that the W and the Z are also at the electroweak scale. Also, the top quark is natural. What is the problem is rather, why is the electron so extremely light?
Yeah. Interesting.
This is because normally coupling constants you expect of order 1, but the electron would be 10 to the minus 5. So this is one of the puzzles. Now, as I said, we have observational evidence for new physics, and they can be explained by extensions of the Higgs sector. And we have these anomalies, which I want to talk about now. So there are 2 in particular. So the first one is indications for new Higgs at 95 GeV, so a little bit lighter than the standard model Higgs. Here, we don't know too much. Here, they just did what they did for the standard model. They looked at their photons invariant mass. There seems to be a peak with around 3 sigma. So this is not sufficient for discovery. For discovery, you require 5 standard deviations. But we don't know yet how this is produced. There's just insufficient information. But however, there's also a Higgs boson at around 152 GeV, and this is more interesting and, as I want to show you, also more significant. So again here, these are similar plots than what I showed you for the standard model Higgs. You see, in fact, here the red peak is the standard model Higgs. And now the question is, maybe in this spectra there is another Higgs. No, I have to apologize to the people on Zoom because this is important and I have to draw it on the whiteboard so that you can easily understand. So what Atlas searched here for is gamma plus X. So like they did for the standard model Higgs, this is used to calculate m squared, the mass of the new particle. And the plus X, this doesn't directly come from the decay of the new Higgs. This is an additional signature. So what we are looking at, for example, is the decay of a new Higgs via some loop, 2 photons, and then it is produced together with X. Now, X We don't know how it is produced together with X. There are different possibilities which we have to study. But what they looked at for is that X could be a lepton, so an electron or a muon. It could also be missing energy. This is called MET. So something like a neutrino or dark matter, or it could also be a top quark and so on. Now, the reason why this plus X is important is because it reduces the standard model background. So remember from the two plots with the invariant mass I showed you, there is a lot of background at low energy, so a lot of accidental events. But if you require that you don't only have two photons, but that you have in addition something else, a lepton, missing energy, and so on, you of course have much less events. So you cut away a lot of events. And if your physics nearly always comes together with X, what you do is you improve on the ratio of signal over background. And this is what counts if you want to make a discovery. For a discovery, the relevant quantity is signal over background. Okay? And in this way, with these additional requirements, you can reduce the background, you improve signal over background, and you have better chances of finding new physics than if you just look at what is called inclusive distribution, where you just say two photons and anything else. I don't care what the rest is. Here you say two photons and at least something. So here, for example, says two photons plus one lepton. Two photons plus tau. Here you can see quite nice peak, I would say. Here is two photons plus two leptons. There's nothing, so this is a constraint. There's two photons plus at least one lepton plus at least one bottom quark. Here you can see again a quite nice peak. Then we have leptonic top decays. There is nothing. We have four jets. There's again some peak. It's not very visible because you have a lot of events, so it's quite shrinked, but the errors are small, so this still counts. Then we have missing energy, more than 100 GeV. There's again a nice peak. For missing energy greater than 200 GeV, there's not much.
So that would be like a neutrino typically or something.
Exactly. This would, also in my model, this would be a neutrino, this missing energy. It could be dark matter, you cannot rule it out, but it could also be a neutrino. Now, my first idea, how could we explain this, was a Higgs triplet model. So probably now I have to go a little bit back to the standard model. So in the standard model, the Higgs, this gauge group is SU3 color times SU2 left times U1 hypercharge. You're still familiar with this, or no?
Yeah, to be honest, no.
No, okay, good. Okay, then I have to go quickly back to this. So the gauge group of the standard model is SU3 color. So this is strong interactions, gluons. Then SU2 left. This is the weak interaction. And the left comes from the fact that it violates chirality maximally. Only left-handed fermions have weak interactions. Right-handed fermions don't have weak interactions. And then we have the U1 hypercharge. And the breaking of SU2 left and U1 hypercharge together, this is then broken down to U1 electromagnetic. But the important thing here is SU2 left. This is the weak gauge group. Now, the standard model Higgs comes in the fundamental representation of SU2 left, so it's a doublet. But there could be Higgses which are in higher dimensional representations of SU2 left. And here the idea was, let's go one step further. Maybe it is a triplet. Now, triplet Higgs contains a charge component. While the standard model Higgs, the charge component is the Goldstone mode. If you add the triplet, you get in addition a charge component. Now, so what can happen here is, if it were a triplet, you would have the neutral component here. This decays to two photons, but it is produced via a W boson together with a charged Higgs. And then this charged Higgs, here we know the branching ratios, how it decays, depending on its mass. And for around 152 GeV, we see it mostly decays to WZ, a little bit to top bottom, and a bit to tau nu. Now, W decays to lepton neutrino, so you can see where you can get missing energy. From the W, you can also get the lepton, and from the bottom decay, you can get the lepton in the beachhead where we have seen the excesses. So here, these are the fits to the individual regions. You see where there is a nice peak. This indicates that there could be a new Higgs. If there's nothing, this is a constraint. But now the good news is, if you combine all of it, you have 4 sigma for such a new Higgs produced in association with X.
Wow.
Now, if you didn't do this plus X, if you just did inclusive, you wouldn't see anything. So this plus X requirement is really crucial so that you can. Yeah.
So all you're saying here is that there's another decay something, but you don't know what that is.
So there are 2 ways of experimental searches.
Yeah.
The first search is what they call inclusive.
Yeah.
And then they say, we have 2 photons, and the rest could be anything, we don't care.
Yeah.
It could be nothing or everything, we don't care. It's just 2 photons, and then you have a lot of events.
Yeah.
But the other way is to do exclusive searches, where you say, I have 2 photons and at least 1 lepton.
Yes.
Or exactly 1 lepton, or some missing energy.
Right.
And if you do this, it's just the probability that you create such an event in the standard model is much lower than just creating 2 photons.
Sure.
So this is how you can reduce the background. And then, I said, if you do it, you can get something like a 4 sigma indication for a new Higgs at 152 GeV. This is not yet sufficient for discovery, but this is only data. So there are 2 experiments at CERN, ATLAS and CMS, and so far only ATLAS looked at this. And now I promoted it to CMS, and they promised me that they will look into this, and hopefully this year they might get some results.
Nice.
Okay, another thing which seems to be quite unrelated, but there could be a very interesting connection, is what's called differential top quark distributions. So remember, top quark is the heaviest quark. Now you can produce this just from gluons. So there's no loop. So you have a lot of top quarks at the LHC. In fact, you can say the LHC is a top quark factory. And now the top quark decays to 99.96%, if I remember correctly, to a W at the bottom quark. In fact, if you have every one of you seen Big Bang Theory, this is the whiteboard of the very first episode. On the whiteboard,
oh, really?
Yes, on the whiteboard of the very first episode of Big Bang Theory, Sheldon calculated the probability of a top quark going to a W and a B quark.
Nice.
So, yeah. So a top quark goes to W and a bottom quark. And now the W could decay to quarks, so hadronically. And hadronic decays of quarks at the LHC are called jets, because they hadronize. So the quarks, they form mesons, and then the mesons enter the detector, and this gives a big shower of events. So this is called jets. Now the problem is, just from proton collisions, you produce a lot of jets. So hadronic decays of Ws are very difficult to see at the LHC. So what we are interested in are leptonic decays of W. So W going to lepton and a neutrino. And then you see you have missing energy here. And if you have missing energy, you cannot reproduce, you cannot construct invariant mask anymore, like for the diphoton. So the signal which they are looking here at is, let me write it again on the blackboard because it's important. So for a top quark goes to W, lepton, neutrino, and a bottom quark, and the same thing happens on the other side. W, lepton, neutrino, and another bottom quark. And now the important thing is W can decay to electron, muon, or tau. Lepton, nearly same probability. Now, a photon can only go to 2 electrons or 2 muons, but it cannot go to an electron and a muon. So this is why what you select here is a muon from one side and an electron from the other side, because there you have much less background, because it cannot come from a photon and it cannot come from a set boson. So what experimentalists call top quark pair production at the LHC is in fact E plus or minus, mu minus plus, plus at least one beachhead. This is what experimentalists call top quark pair production at the LHC. So they don't really see the top quark, they see two leptons with opposite sign, different flavors, and at least one beachhead. This is what they see. And now from these distributions, you have to look, was this really a top quark? Okay? And now the idea here was, because you cannot reconstruct this invariant mass, is that a model like this here, where you generate a heavy Higgs decaying to two lighter Higgses, which one goes to WW and the other one goes to two bottom quarks, has the same experimental signatures as TT bar production. So you see it's the same final state, and because there's nothing peaking, this could be a contamination of your standard model measurement for top quarks. Now, Atlas did such a measurement for the differential distributions of top quarks. So here they looked again at the invariant mass of the electron-muon pair. So this is like the invariant mass of the photon pair, but it's not peaking because you don't have a direct decay. It's Lorentz invariant, but not peaking. You can also look at delta phi mu. This is the angle between the electron and the muon. And now what you see here is the dashed lines is what Atlas measured. And they measured Monte Carlo. This is principal standard model prediction over data. And now you see if you have one, the standard model is in agreement with the measurement. If you don't have one, then it's not in agreement. Now you see these dashed lines are always below one, but since it's standard model over data, below one means too many events. Okay, so we have too many events at low masses and low angles, and too few events at high masses and high angles. But these are normalized distributions, so they're normalized to the total cross-section. So this means if you put more events at lower masses, lower angles, you also explain the deficit at higher masses and higher angles. And now you can see here is dashed. This is what Atlas measured, and it's in quite poor agreement with the standard model with one. Now, if you add new physics, this is the solid lines, you do much better. So if you add new physics like this here. And now, if you look at this table here, you see the agreement with the standard model was horrible. So normally you expect a chi-square of 1 per 1 degree of freedom, but you see here this was absolutely horrible. But if you add new physics, you are doing better. And depending on the standard model simulation, which has some uncertainties, you are at least doing 5 sigma better than the standard model.
So the new physics you added was the 95 and also the 152?
Exactly. This is what I'm coming to now.
Okay.
So I added a new Higgs boson. I don't know mass yet, could be around 300,
Okay.
decaying to 2 lighter Higgs bosons. And now the
But when you added the new physics in the Monte Carlo, you have to say what the middle Higgs boson is, don't you?
Yes, but since they measured the invariant mass of the electron-muon pair and this angle, this is nearly only sensitive to the mass of S and very insensitive to the mass of capital H.
Okay.
So for determining the mass of capital H, they should measure the invariant mass of electron-muon BB bar. But they didn't do it yet.
Okay.
So if they measure electron-muon BB bar, then we can get a better handle on the mass of here. At the moment, mostly it's the mass on this one here.
Okay.
And now, thanks for taking away the point already. So this is introducing the point, sorry, wrong wording, introducing the point. So this should be 95. And the reason just is a 95 GeV boson cannot decay to WW, CC, or top, because they are just too heavy. So the only open channel here, the first open channel is BB bar. So for 95 GeV boson, you expect that it mostly decays the bottom. This one, 152, this can decay nearly to WW, so it can still off-shell decay to WW. So this could be 152.
Oh, I didn't appreciate that. So they don't have to be the same.
No, they should in fact be different.
Okay.
Because if this were both times 152, you would get 4W, and that's too much. You don't want 4W bosons. The constraints are too big, too good. So
Oh, there'd be a possibility to get 4W.
So if this were 2 times the same,
Right,
you would have the option that both decay to WW,
right,
and then you have 4W again,
Right,
and that's
okay.
very constrained.
Okay.
So what you would like is that this is 95 and this is 152.
okay,
And now what you can test is it consistent with 152? So you vary the mass of the Higgs going to WW, and then you see, is it consistent with 152? And in fact, what you find is you find something like 143 to 156 is the 1 sigma preferred range. So it is compatible with a 152 GeV boson.
but it's got to be pretty wide if it's going to go to 2Ws. If it's less than 160 and it's going to 2Ws?
Yeah, one of them is off-shell.
Okay.
It's going to an on-shell W and an off-shell W.
Oh, okay,
But it's still the dominant decay.
okay.
It is still dominant. Okay, so this is just, I don't think I should get into too much details. This is just to show you we have a UV complete model, which gives rise to the signature. And then I think we can already get to the conclusion so that we still have time for questions. So here, was this list of anomalies, which I wrote in the article by Scott contacted me. So you see, in the meantime, already 3 anomalies got killed.
Well, okay.
You don't try, you mean, okay, the X17 could still be there with reduced significance, that's true, I agree. But what you can see here is each anomaly is pointing to some extension of the standard model. And from this point of view, I think one can say the standard model is crumbling. So scalar, the S scalar stands for new Higgs boson. So you see there are a lot of errors. So maybe one of these hints for the Higgs bosons, which I've told you about, hopefully the 152 GeV boson will be confirmed in the not too far future. And I thank you very much for the attention and look forward to questions.
Thank you.
Well, I have some questions. I mean, you also talked about other potential Higgs bosons at a higher scale in terms of dijet anomalies,
Yes.
di-dijet
I'm
anomalies.
not sure if I would call them Higgses, they are rather diquarks.
Oh, okay.
I mean, there are still extensions of the scalar sector, but because they are charged under color, I would call them diquarks.
I see. Okay. All right. So these are the only Higgs extensions, these two, of the anomalies that you looked at.
There are also some indications for charged Higgs at 375, but it doesn't pass the 3 sigma threshold yet. It's only 2.8 sigma. And there are also some more indications for a new Higgs at 420. But once you include this look elsewhere effect, so just the probability that if you look at a lot of observables, the more observables you look at, the higher probability is that there's a statistical fluctuation. It goes below the 3 sigma. So only 95 and 152 are above the 3 sigma threshold after you included the look elsewhere effect. This doesn't mean there cannot be more. There can still be more, but yeah.
So I have a question about these crossed out nodes on your diagram there. So every 6 months or so, I see some news article on my feed saying the LHC has discovered some new bump, right? And this is a hint for new physics. But then after about a month or two, eventually the bump kind of goes away. And so are these crossed out things bumps that went away when more data was taken?
No,
can you explain this?
These are not, 2 of them are not LHC anomalies. So the anomalous magnetic moment of the muon, this is just the precision observables. We have measured the G factor of the muon. And here the problem was apparently that, so I have to be a bit more careful. So they measured this anomalous magnetic moment of the muon already at Brookhaven, and then the measurement was confirmed at Fermi. So the direct measurement doesn't seem to be a problem. However, for the standard model prediction, you either need simulations via lattice QCD, or you need experimental input. So the problem is this diagram here, where you have the photon, then you have another photon. Okay, so here muon, and then here you can have quarks inside the loop. So you see this diagram here. So this is a photon, and it has a vacuum, what's called vacuum polarization. There are quarks inside here, and this is non-hadronic. And now you can calculate this on the lattice. This is of course very difficult, or you can get it indirectly via analyticity from E plus, E minus two hadrons. So you do E plus, E minus, with a photon going to QQ bar. So this is hadron. So from this cross section, you can get information here. But now what it seems is that in measuring this, they forgot about photon corrections to the initial states. And this would have led to a wrong standard model prediction. So not including these corrections on the experiment would have led to wrong standard model prediction. This is probably the explanation of the T-2.
I hadn't heard that. I hadn't heard that last bit of it. I had heard.
Last bit is not official. This is internal information I have from my friends in the hadronic community.
You think
I
they
see.
calculated it wrong, essentially?
No, it's just they didn't nobody calculated it because the experimentalists thought they took it into account, but apparently they didn't take it into account. So it was just not included. Yeah. So this
What I had heard before was that there's, how many measurements of that? 50 measurements of that in the, a lot of measurements over the years.
Yes.
And then there's a recent one in Russia or something that
Yes.
was different than
Exactly.
all the other ones.
Yes.
Right? And
But there's
So-
there's important difference. The measurement in Russia was they were able to tune the energy of the electrons because you need this cross section at different energies. You need the energy dependence. And there they were able to tune the energy of the electrons. In the old experiments, they couldn't tune the energy of the electrons. They needed initial state radiation to get to different energies, so that the electron emits a photon, loses energy, and then you have an event with different energy. And this leads exactly to this problem with the initial state radiation. So the Russian experiment is the only one which doesn't have initial state radiation.
really,
problem.
it's the only one.
Yes, it's the only one which
Oh.
doesn't have, where they were able to tune the energy. All the rest was with a fixed energy.
Interesting. Okay. I didn't know that. Wow.
I mean, I also, as I said, these are things you only hear at conferences talking to the people. These are not things that go out in a press release.
Right.
Wouldn't be politically correct already at this stage to say this, yeah. So this is what
I saw one of your talks before, this is 4 years ago or something, like a talk you gave where this had not come up yet, I think.
No, this was within the last year.
Right, because in that talk, what you were saying was this other Russian experiment came in, but there's all these other experiments that disagreed with it.
And the Russian experiment also.
Maybe it had, maybe the Russian experiment hadn't come in.
You mean
But
the
the
W calculation.
lattice
that's
calculation had
yeah.
come in, and they came out with this thing, and you said, well, look, it's either wrong on the magnetic moment of the muon, or it's wrong on the cross section.
Yeah,
It can't be, so it's, something's wrong.
yeah.
But this changes the whole story.
Yes, so it was exactly like you said. There were so many measurements of hadronic light by light that people thought this must be correct. So people didn't consider the option seriously that there could go something wrong with these 50 measurements, as you said.
Right.
But apparently it seems like there's a common systematic for all these measurements.
Interesting.
So, but this is also my hope for this for this 152 GeV boson, because what I like to say is this measurement is so easy that even experimentalists can do it correctly, because you only need to pick a background and you need to look for a peak on it. So all the stuff here with T-2, this is orders of magnitude more complicated experimentally and also theoretically than bump search. So bump search is really the easiest stuff you can do. Now here there was more data, and it seems that this, which was a non-resonant excess anyway, might not be there. And here there was this is also hadronic stuff. So here there was always the question: could this be some hadronic stuff again? And there was a new measurement at PSI where they didn't confirm it, but they also didn't completely rule it out. It's just less likely that it happened. But concerning the peaks at the LHC, I think there was not much since the famous 750 GeV disaster. So something like 7 years ago, there was this big hype on a new Higgs boson with 750 GeV decaying to 2 photons. And this was a mixture of statistics and an experimental mistake. But again, of course, this is only what you hear talking to people. Nobody ever made the statement that there was a mistake, but they misidentified jets as photons in their event. But anyway, so the 750 GeV, this was around 3.5 sigma or so. But for me, there were 2 problems. First of all, a Higgs with 750 GeV, you don't expect it to decay to photons. You expect it to decay to WW, ZZ, and TT bar, not to photons, because the other channels are already open. The second problem was, it was at the end of the spectrum, so you couldn't interpolate, you had to extrapolate. So the 750 was, from this point of view, I would say, more delicate than 152. 152 is very much in the proximity of the standard model Higgs. So I would say anything that could go wrong for 152 should have already gone wrong for the standard model Higgs. So there we really, I would say, we need more statistics.
So in a model that just adds the 152 and the 95, you can just add that to the standard model without causing any problems. Or does it cause other?
But you have to always check for vacuum stability and these things, but they are already not great in the standard model. So, and you don't expect it to be the final theory. So this is not too big problem, no.
Okay, any more questions? All right, let's thank Andreas again for the nice talk.
All right, that was great. That was great.